Sorry about that. We're going now. All right, so this is really important, what I just wrote here, right? So that's why so if you just start writing the equations with the currents, rather than by defining voltages like this, then I'm thinking about too many minus signs in my head at once, I think. All right, my brain can't handle that. I like thinking just in terms of voltage polarities first, and then I start plugging in the current separate, okay? All right, so then if I get to V4 here, so it's minus V4, so I'm gonna say minus again. But which current goes into the plus terminal on that guy?
I2.
I2.
I2. So I'm going to say minus I2 minus I3, because I3 comes out of it, okay? Or comes out of the plus terminal, times R4. And then V6, I only have I3 going into the plus terminal, so it's I3 times R6, like that, okay? Then I can simplify this guy down if I want to 0 equals, then I'll multiply it through, right? So I'll say minus I1, well, you guys understand, this is algebra at this point, right? I'm not going to waste time on this, right? But I find it easier. You guys will try to jump to those equations with the currents, and I find that hard, all right? At least in my mind, all right? And I know that when you're looking for a specific current, I1 is 1 amp, I2 is 6 amps. When you start trying to give those answers, chances are you're going to be wrong a lot. All right, so it's important to check that. All right. Questions about that? This is an important point. Okay. All right, so I'll move on then. All right, so where this gets tricky is when I have a quote unquote super mesh. All right. This is like in the nodal method, I had a problem when did the nodal problem have problems? And what defines a supernode in the nodal method, right?
Voltage source in between two nodes.
Voltage source in between two nodes is a problem. Why is it a problem? What makes that a problem? Somebody other than Stephen.
Because one of those nodes isn't your reference node.
Well, so yes, that's problematic, right? But the real issue is when I'm doing the nodal method.
Oh, you can't find the current.
Can't find the current through it, right? I'm solving for currents when I do that, and I don't have any way to find out the current. So in the super mesh method, when I'm writing KVLs, current sources give me a problem, right? Why is there a problem with the current source?
Because you can't find the voltage.
Can't find the volt. Well, I can, but I can't. There's no relationship that tells me for a current source what's the voltage across that current source. The circuit tells me that, right? There's no way there's no relationship at the terminals. Like for a resistor, there's a relationship that says if I know the voltage, I know the current. For current source, if I know the current, I don't necessarily know anything about the voltage. There's no direct relationship there. The circuit tells me that. If I put 1 ohm across a 1 amp current source, I got 1 volt. If I put 2 ohms across it, I got 2 volts, right? So it's the rest of the circuit that tells me that. So what that does for me is it says, all right, well, if I have, so basically the issue here is current sources cause problems in this case. Current sources cause problems because I don't know their voltage. So what that usually says is when I'm looking at a picture like this guy right here, you know, I've got I2 and I3, that says that if I tried to write a KVL around, this is the way to do it, I guess. If I tried to write a KVL around that top mesh right there, so I2, so the I2 mesh, right? If you look at that, what would I do? If I define this guy, let's say like this, V3, V2, V4, like that. What would I do for the current source?
You can't
You'd
do
make
anything.
well, yeah, but you would just, wouldn't you say I2?
I got to call it VX.
Okay.
Okay. It's just in terms of if I'm writing a KVL with that loop, I just got to call it VX, right? And I don't have any way to define anything for it. Okay. So if I just went around that loop, you know, I could totally write a KVL for the top mesh and for the bottom mesh, right? I could totally do that, but in both cases, it's just like the other day. Okay, if I have a voltage source that is in a supernode, there's a current going through it. And we basically wrote a KCL at each of the two nodes and got rid of it, right? That's the approach. And the same thing is here. I would write a KVL for the top mesh and write a KVL for the bottom mesh. And then I would basically set the Vx values from the two equations equal to each other, right? So if I looked at that top mesh right there, I would have 0 equals minus V2 plus V3 plus Vx minus V4, or sorry, plus V4, all right? And then if I did it for the bottom node, right? So for the bottom one, let me do it this way. For the bottom one, I would have minus V5 minus V4 minus Vx plus V6. I could basically solve this bottom guy for Vx and then plop him back into here. If I did that, that would be equivalent to doing a KVL around that outer loop. Okay. So basically when we do this, we basically say, forget that that middle loop is there. Okay. So basically what you do is you do KVL around the super mesh, right? Which is the combination of the two meshes. All right, so it's the combo of the two. And then the other step that I worry about here is what? Yeah, so this auxiliary equation or whatever that relates these two guys. So Aux equation. In this case, given what I have right here, what would the relationship be? All right, so somebody online. This gets disjointed when it's. I know.
I2 minus my 3 goes I0.
Yeah, I0 is I2 minus I3. Right, just looking at the sign. So basically, you know, which arrows are in the same direction and which arrows are in the opposite direction, right? All right, so we're going to use that in some examples here coming up, all right? But I wanted to just make sure we covered that. I think you guys are comfortable with mesh and nodal for the most part, all right? Where the mistakes come in, and they come in a lot, is because of the signs, all right? You know, and always check that the KVLs that you write, all right, always check that these KVLs that you write. So if I go back to this example here, that I always have an I times an R, all right? I better always have voltages in all of my KVL equations. Just like in the nodal method, all of my terms better have what units? Better have amps, right? They better have amps, okay. All right, so, all right, I want to talk now, my second point today, and again, I'm going to use the mesh stuff as I go through here, but my second point today is to look at some more Thevenin and Norton stuff, okay? And then we're going to use mesh to solve those. All right, but the whole idea, I talked about this equivalent circuit concept, really useful and important idea that we talk about all the time, which is to say, if I have a network comprised of a bunch of stuff, right? The example I gave is the whole North American power system is one example. Another example might be if I've got an electronic system, which is made up of all sorts of parts. I can still think of that thing as a voltage source and a resistor, or a current source and a resistor, right? I can think of them both ways. Okay, so what we say here, and this is important. So if I look at this this guy over here on the left, right? So if I look at this thing on the left, there's a bunch of stuff there. Basically, what we're saying is all I need to know is the terminal characteristics of that thing. Okay, meaning if I draw 1 amp from this network, what does that do to the voltage of the terminals? Right? That's basically the idea. So what we said is I need two things here. I need to know VOC, which is the voltage before I connect the load. And I need to know the resistance, quote unquote, seen by the load current. Right? So the resistance seen by it means that if I were to go and look at this circuit here, and I were to apply a source of some kind, let's say a current source, right? I would say to myself, well, what is the effect of that current source? What resistance does that current source see? right? So if I've got a bunch of crap in there, basically it says, well, how do I combine all that crap to figure out where that current is flowing and what voltage drop is going to be created by that current? Okay. All right. So there's two components. VOC is basically the impact of all of the internal sources. And then REQ is the equivalent resistance that is seen by a load, right? And its impact is there because of the load itself. And so the thing we talked about here, if I think about this, if I looked at that circuit right there, I could look at this guy by superposition, right? And I could say, if I did by superposition, what is the component I get for the voltage V looking at that circuit if I just looked at the voltage source?
Is a VOC?
VOC, right? The component of the voltage I get at the terminals in this case is, from VOC is just VOC, right? What's the component that I get from that current source?
It's a negative times I.
Yep, I times REQ, like that, right? And I know it's negative because if I short out that internal source, and here's this guy right here, this test source I that I hooked up here, there's going to be a voltage created across that guy like that, right? So if you think about what's happening, basically that drop is basically causing a decline in the voltage if I ran this circuit. So what that says is, kind of in theory is that the load current causes the open circuit voltage to drop, causes the voltage of that terminal to drop from its open circuit value. So it's the effect of that load current. It's how that load current affects the output voltage.
That load current is I short circuit, right?
No, that load current is that load current. All right. So let's look at an example. Okay. So let's look at this circuit right here. Okay. If I said to you, okay, so what's VOC in this particular circuit? So this guy's open circuited. How would I figure out VOC?
Voltage across R2.
Voltage across R2. Where'd it go? There we go. Voltage across R2. Now in this case, why didn't R3 count?
Because there's no
Zero, zero current.
There's no current. It's open circuit, right? There's no load over there, right? So there's no I. So that means VOC is the voltage across R2. So what would that be in this case in terms of the components I've got here?
R1 plus R2 V over R1 plus R2, sorry.
Yeah. So can I keep it to the people online? Okay. My brain's getting overloaded. Okay. I don't mean to squash Eli's enthusiasm here, but so this is a voltage divider, right? So if I had a voltage divider, Tony, you said it R1 plus R2 goes on the bottom, right?
Yep. And then
My way of thinking of it is that's the current that's flowing. And then to get the voltage, it's that current times R2. Like that. All right, now, if I said to you, looking at this circuit, how would I then try to figure out the equivalent resistance?
You can turn off the voltage source and then look through the terminals.
Yep, for REQ, what I would do is turn off the source. So basically you turn off VS. So if I have a voltage source, by turning a voltage source off, what do I do to it?
Short circuit.
Yeah, in fact, I think of it probably in two steps. VS equals 0. So turning a voltage source off means setting it to 0. That is, if I have a device that has 0 volts across it, that is a short circuit. Okay, so that says turn this network into, here's R1, here's R2, like that. Here's R3. So what would it be in this case? What would be my REQ?
R1 in parallel, R2 plus R3.
Yeah, so a current flows into that terminal. It would go through R3 and then it would split, right? Because R1 and R2 are in parallel. So in this guy, I can see REQ should be R1 in parallel with R2 plus R3, okay?
How is R1 parallel with R2 if they share the same current?
R1 and R2 do not share the same current in the circuit here, All right, so they shared the same, when I was calculating VOC, this is a question people always get confused by. The VO, so looking at the circuit on the left that I've shown here, right? If I look at that particular circuit, there is no current flowing through R3, all right? R1 and R2 are in series in the circuit shown on the left, okay? However, when I'm looking at trying to do, let me do REQ on a different slide, all right? When I'm doing REQ, I turn off the source, and here's R1, here's R2. This is a question a lot of you guys have and probably aren't asking. Okay, if I'm looking at that circuit, the question I'm asking myself is, if I hooked up a source at the terminals, where would the current flow? Right, so when I look at that circuit on the left, I can see that R1 and R2 are in parallel with each other in that circuit. All right, so in this case, I can see that the equivalent resistance that I see looking into those terminals is the current coming in here, I test, if you will, the current I test will flow into R3, and then it will enter, that current enters into the parallel combination of R1 and R2, and then leaves back out, okay? This is confusing. This network is different than the one that I showed on the left here on this slide, all right? Yeah, they start out with the same network, but effectively they're different, all right? And that's a really important point. So let me look at this. Let's go with that same idea. What if I had dependent sources?
You can't turn off the dependent source.
So
You can add a test source.
dependent sources, there's two ways to do it. I don't like to do it the way you guys do it, but I'll do it the way you guys do it. All right. So let's do that. If I had this circuit, same one. What Steven said is correct. One of the ways to approach it is to apply that test source. Okay. So let's say I applied a test source here. This goes back to my basic idea here is when I look at this REQ is the effect. It basically is trying to tell me what effect does a load current have. All right. So when I want to see what effect a load current has, I use the superposition principle and I say, well, let's short out VOC. Okay. So that's basically what we do here is we say, all right, well, when I have this, when I want to figure out what a load current does, I take I test and apply it here. Okay. And I turn off all the internals. So I have this. Notice this is the same way as I was trying to think of it here, right? That's what we do is we say, if I don't have dependent sources, it's just a simpler thing to do to not apply a test source, but you're always applying a test source. In theory, even when you try to simplify this network like I have right here on this slide, I'm still in concept applying a test source, right? Because what I'm saying to myself when I apply a test source is, well, if I want to figure out the resistance that I see looking into this network, which I call REQ, to figure out what that resistance is, I apply a known current and I try to figure out what?
Voltage.
I try to figure out the voltage, right? And I know when looking at this picture, if I know V test and I know I test, R test has to be equal to V test divided by I test. Like that. All right. That allows me to figure out how this works. So if I said to you, okay, let's do that. Let's figure out V test for what I just showed right there. All right. What would that be? Oops. Yeah. So looking at this, so somebody online, tell me, so if I want to, and somebody other than Steven's got this, right? V test equals I test times what?
Equivalent.
The equivalent resistance of R1, R2, and R3.
Yeah. So what is that in this circuit? What is that?
R3 plus R1 and R2 in parallel.
Yeah, R3 plus R1 and R2 in parallel. All right. When you look at it like this with that current source connected there, it's pretty obvious, right? And then if I want to figure out what REQ is, I shouldn't call that R test. My equivalent resistance is REQ, right? I say REQ is equal to V test, which is this guy here, I test, divided by R3 plus R1 in parallel with R2, all divided by I test. And so look, I got the same thing that I got by just looking at that circuit by inspection. All right, now they may have taught you that in network 1, but you didn't know enough yet to know that you didn't know anything. All right, so you know, it's, a lot of those things that they teach you the first time around are lost on you, right? It's once you got some experience under your belt that you start to realize, oh, now I begin to see how these things kind of come together. Okay. All right, questions about that?
So that works for dependent sources?
It works for anything.
Hmm.
Okay.
Good to know.
We have to apply the test like this when I have dependent sources, because dependent sources are weird. Dependent sources, you know, they depend on other things within the network. So I can't just turn off all the sources and just say, well, what resistance would a current source at the terminal see? I can't do that approach in that case, because there's dependencies that exist, right? So there's two ways to approach that problem. One of them is this way, to apply a test source. The other one I'll talk about here in a little bit. So Christian, I don't know if I answered your question or just made you more confused.
No. I see the relation. I'm so used to doing VOC divided by I short circuit.
Yeah.
But this makes sense now that you've explained
That's
it.
the way I always do it, typically. You can do it either way. Okay. So one thing to remember is, okay, so there's the Thevenin equivalent and there's the Norton equivalent, and they are equivalent, all right? And if I look at this, the Thevenin equivalent basically says VOC and RTH are in series. The Norton equivalent says I got a current source in parallel with those. Now, you guys would say this is source transformation to go from one to the other, right? If I look at this, the important thing for me is if I look at the terminal characteristics of these guys, meaning if I look at the voltage current relationship that exists right there, they are identical for these two circuits, okay? And for that reason, if I look at this guy over here, let's say the circuit on the left, right? If I said, what is I short circuit in this case, right? What is I short circuit for the guy on the left?
VOC divided by RTH.
Yeah, VOC divided by RTH. If I look at this guy over here and I said, well, what is VOC in this circuit? The open circuit voltage.
I short circuit times R Thevenin.
I short circuit times R Thevenin, right? So these are entirely equivalent values here. All right, that's what makes these guys, I get the same relationship from both pictures. And so for that reason, there's a couple of approaches we have with these, right? So if I have, and this guy, approach number one only works with no dependent sources. All right, it does not work once I have dependent sources. All right, so I turn off all the independent sources and just simplify the network. All right, approach number two is to find the short circuit current and the open circuit voltage. Because of this relationship, which exists from what you guys call the source transformation, because of this, one way there is always this relationship, VOC divided by I short circuit is always equal to the equivalent resistance seen looking into that network. So one approach is to say, well, I can find both the short circuit current and the open circuit voltage and relate them that way. The other is to apply a test source. Technically, 1 and 3 are the same. Okay.
So if there is dependent source, we can't turn off everything. I mean,
We'll get to that question. When I apply a test source, I am only trying to see the effect of the current from the load. This is maybe the important point. All right. The equivalent resistance we see, all right, the equivalent resistance we see is the effect of a load current. All right. And so the way to think about this in general is VOC is the effect of the internal sources. The R equivalent is the effect of whatever the load current is. So if I'm trying to find just the effect of the load current, I then, by superposition, need to turn off all the internal sources, right? To get this equation that I wrote right here, I use superposition to get that equation. All right, so I turn off VOC to find the effect of I. I turn off I to find the effect of VOC, right? That's the basic principle to tie these guys together. All right. All right, so let's, and first of all, one of the questions that people ask a lot, let me just take so if I have a dependent source, right? There's 4 kinds of them. And we're going to start on with some of those today because this is where it gets interesting, right? So this guy here is, let's say, A times Vx, and Vx is some other voltage somewhere in a circuit, okay? This is a, what kind of dependent source is this guy right here?
Control
Voltage, yeah.
Voltage controlled voltage source, all right? There's basically 4 different varieties. Well, guess what? There's actually more than that, all right? There's all kinds of crazy stuff that I could come up with, okay? If I were to take a generator, for instance, right? Like if I had if I go over to a Duke power plant, right? And I see a generator spinning, there's a voltage that I see at the terminals of that generator, obviously, right? Because that generator is the voltage source that powers the network. Anybody know if you take a motor, or if I take a generator and I speed up how fast it's spinning, what happens to the voltage in that case?
Should increase.
It should increase. That's correct. Who said that?
Me.
Okay, me said that. Okay, all right. So if in that case, so based on whoever it was whoever me was that said that.
My name is
what does
Chris,
that
by the
mean?
way.
If the speed goes up, and that it causes the voltage to go up. If the speed goes down, what would happen to the voltage then?
Well, the inverse.
The opposite will happen, right? It'll go down. So that kind of says that in that generator, I could think of him as a dependent source, couldn't I? K times speed is equal to a voltage, right? That's the concept of a dependent source in my mind, right? So if the speed of that generator affects what that voltage does, that's the dependent source idea. I can think of all kinds of places like this. If you go and get a voltage sensor, right? Let's say I had a voltage sensor, one of my favorite voltage sensors. If you don't have one, LM35 is my favorite. All right, so LM35 is a voltage sensor. Look it up. That guy, what do you think he does? Senses temperature, right? And it'll be K times the temperature is the voltage he gives me, right? So sensors operate like that, right? They're dependent sources, right? And you guys learned about voltage dependent, current dependent. You learned the 4 varieties that we see. They happen a lot in electronics. So transistors, which you'll learn about in electronics, are voltage dependent current sources. All right, and so you'll learn more. There's reason. One of the things people ask about is, well, why do we learn all that stuff? You can see a resistor, you can see a voltage source, right? It's hard to see a dependent source. There is no such thing as a dependent source. Just so that we're clear, there is no such thing as a dependent source. The LM35 is a temperature sensor. The model for that thing, the mathematical model that allows us to design things with it, is a dependent source. Okay. All right. That's the thing. Is dependent sources are not real things. They're models for real things. Okay. You can't go to the store and buy a dependent source, but you can buy a generator, and you can model that generator in your circuit as a dependent source. Okay.
So that relation is higher temp, higher voltage?
Yeah. Higher temperature, higher voltage. There'd be some, what I call gain, some multiplier here, right? That tells me if the temperature goes up by 1 degree, how much does the voltage increase?
So that's just a random coefficient.
Yeah, so the manufacturer would specify that to you, right? It depends somehow based on the internals of that device. Just like for a generator, it depends somehow on the physics of the generator to tell you what that relationship is between the speed and the voltage.
And I presume that's how geothermal power works.
That is how, yeah, that's basically how any kind of device sort of works. Is there is this kind of what I call energy conversion between a mechanical thing and an electrical thing that happens. So yeah, anyway, I throw that in there because dependent sources rattle people's brains. I know, because they seem weird, but they're models for things that happen and things that, if you think about it, you've experienced before. Okay. All right. All right. So all that said, let's take a look finally at an example. Okay. So let's say I want to find the Thevenin equivalent for this guy at the terminals A, B. Okay. So if I want to do that, what's my step number one? Well, so I have two places. So this guy has a dependent source, right? So this dependent source is always kind of denoted with the I don't know a squarish thing. That's a rhombus or something. I don't know what you would call that, but it's a squarish looking thing as opposed to a round one. Independent sources are round. Dependent sources are always kind of squarish. If I have something like this is a case where I can't just try to find the equivalent impedance by looking into the terminals, right? Because I have a dependent source. So what I said is I got to try one of those other two methods. So my typical approach is to use this guy, VOC, ISC, and then relate those two. That's my typical approach. That's not the way you guys learned it in Zybooks. And so I want to be careful. I'm going to follow your approach. All right, the second one here. So I find VOC, apply a test source, and then solve for whatever terminal variable I'm not applying, and then use this approach here to find Z Thevenin. Okay. All right. I'm going to use the bottom approach here, but it doesn't matter. I mean, my step one is the same either way, right? I got to find VOC. So, all right. So if I'm going to use, so first thing I'm going to do here, I want to find VOC. Okay. So if I want to find VOC, what should I do? So let's say VOC is that voltage, right? How should I approach that here?
Can you simplify your circuit?
Yeah, I want to simplify this circuit a little bit. Now, I don't know, Stephen, what you mean by simplify. What's your approach for simplifying it?
I would probably find the impedances, put those together. I'd probably do a source transformation and then find the voltage.
Okay. I knew you were going to say source transformation. I would not do that here. You can't do that here.
Okay.
Because you're
For the
screwing up the
capacitor,
circuit.
right?
You're screwing up the circuit now because I naught is the current through a branch here that you're going to end up moving around if I do
you're
source
correct,
transfer.
yes.
So I can't, in this case, I'm going to leave it there. All right. I don't, anytime I'm doing things with dependent sources like this, I don't do any simplifications like that. If I thought hard enough, there might be some cases where you could do that, but I just say that I don't want to do it because I know that I can make a mistake. All right. Again, that's where I just say, I know I'm a simple man. I keep things simple. Okay. So if I look at it this way, I would do exactly what Stephen said though, and I would simplify this guy down. So I'm gonna have two impedances, Z1 and Z2. I don't like, especially capacitors and stuff, they get a negative in their impedance. Right? So I got negative 4J. What does negative 4J mean? Why do I have a negative? That's weird, isn't it? What's a negative sign mean?
Angle is negative 90 degrees.
The angle's negative 90 degrees. All right, that's all it means, right? So, those negative signs mess me up because they really are going to screw up your day later on when you're trying to write your passive sign convention stuff. All right. So for me, I would say Z1 is 2 minus J4, and I would say Z2 is 4 plus J3. Okay. So I would make that distinction right there, and I would draw that circuit like this. Okay. So I replace those two guys, right? I replace those impedances. And then this guy over here, if we look back to the circuit, 15 angle 0 amps. I don't keep the angle there when I have 0 degrees. Right? I just call it 15. Okay. Now, keeping with what I've said before, right? I just write V1 and V2. I define my voltages. That's kind of a first step for me. I like to figure out the voltages across things. Okay. So if that's my circuit, let's find my VOC. Okay. How should I go about, and let's remember this guy was my I naught here. All right.
So could you figure the current of I naught by current division of impedances with
I don't,
This one?
yeah, so that's a good thing. I don't know that here though, do I? I don't have a current divider per se. I kind of do, right? There's that 15 divides between two branches,
Yeah.
but I have a current source in one of those branches.
Uh,
All right, so it's not a current divider in the normal sense where I just have straight impedances. So what should I do?
Use
For
mesh or normal.
analysis.
You know the I naught because I naught equals I source.
I naught does not, so I source you're saying is 15?
And I know I source equals I naught plus to I V2 I
Yeah.
Z2.
This is a case where, first of all, if I look at this, VOC is the voltage across that current source, 0.5 I naught, right? That is the voltage across this guy, right here. All right. This is a case where it's not really clear to me that I can do mesh and, that I would call it mesh or call it nodal. This is a case where I have to figure out some way of coming up with the relationship here for that 0.5 I naught, right? So if I look at this, I guess what do I want to call this? I guess what I would call this here is I would say, well, if I looked at this top node right here, right? What would KCL be at that node?
V1
If-
over Z1.
Let's just do KCL in terms of the currents. I have 15 going in.
It's equal to I naught going out and then 0.5 I naught.
Exactly. Right. In this particular case, 0.5 I naught is essentially what the voltage is across that, or sorry, 0.5 I naught is because of the open circuit here, the current in this guy and the current in this guy have to be the same. All right. So 15 equals 1.5 I naught. Like that. Okay. That helps me some, right? That tells me right there that I naught is equal to what? Well, it's 15 divided by 1.5.
I'd use my calculator for this. It's 10.
Yeah.
So would this mean that, because I naught is a phasor, right? So this would have an angle of 0 degrees.
It would have an angle of 0 degrees, yes. I'm being a little bit cavalier about that. I'm not using that, but I don't need to, right? Because in this case, it's got an angle of 0 for the source. Okay. All right. Now,
Sorry.
What's that?
Is there a relation between the impedance and the level of current that's going into
No.
that line of impedance? Okay.
No, there isn't, because it's basically like I have a current source that has pinned the current in this branch right here.
Okay.
All right. So in this case, now what would I do to figure out VOC?
So you do the math 2 on the right.
Okay, so I'm going to do a KVL, and I'm going to say 0 equals, as I've written this, minus V1
Plus V2
plus V2
plus VOC.
plus VOC. Okay, so that tells me that VOC has to be equal to what? V1 minus V2. Okay, and so that would be I naught times Z1 minus V2. V2 is in this case, what's the current through V2?
10.
I naught.
It's
0.5.
0.5 I naught, right? Minus 0.5 I naught times Z2, like that. Right? And then I could just plug in to figure out what VOC is. All right. If I go through that approach, all right, what I find is that it becomes, in this case, negative 55J. All right, negative 55J. Let's say I want to write that in polar. Right. I'll give, as before, I'll give you my MATLAB code where I solved this, right? But what is that? Negative 55J. If I want to write that in polar, what would that be?
The 55 and negative
Negative
90
90, right?
Minus 90 degree.
Minus 90 degrees would be the angle, yeah. Right? Because minus 55J, the way I think about that is minus 55J in the complex plane would be pointing down here. Right? So that means that guy is at an angle of negative 90 degrees or 270 degrees. Now you'll notice in MATLAB on your homework, I always say plug in an angle between 180 and minus 180. Right? That way, when you put in 270 degrees, it doesn't tell you it's wrong. Right? That's why I do that. All right. It's just to make sure there's infinitely many correct answers for the angle. All right. That's, I always just constrain it to be between minus 180 and 180. Okay. All right. So moving on. Okay. So now I want to, this case, I want to apply a test source. All right. To figure out the equivalent impedance. So, all right. If I want to find the equivalent impedance, I'm going to apply a test source. What do I do with all the sources inside?
Turn off the independent.
Turn off the independent sources. So basically what I want to do is I'm going to say, here's my Z1. All right, I'm calling this V1 still. This guy was defined as I naught. Okay. Here is my Z2. Here's that dependent source, 0.5 I naught. And I'm going to apply, that's probably writing on the screen. Okay. I'm going to apply a test source here. Okay. Like that. All right. Now, I'm going to say I put a 1 volt test source on there. Okay. Now,
Specific reason you picked a voltage source instead of the current source that we did when we were explaining?
I can pick either one, right? If I make a voltage source, I solve for the current. If I make a current source, I solve for the voltage. Okay. So if I do this now, what I want to do is, so I don't know, any ideas? How should I approach this problem? My goal is to find the current in flowing into this circuit. All right. And specifically, you know, when I want to do this, Z Thevenin, the equivalent impedance looking into here, is my V test source divided by the current I test, like that. Which direction is that? So in this case, my V test is 1 volt. Okay. Which direction is that current going to be? By definition.
Negative.
Negative meaning what?
From the bottom to the bottom.
Yes.
I test would be this way. He would be leaving the source going into the circuit. Okay. Be leaving there and going into the circuit. Right. And the way to think about that is basically if I had this picture here, I'm going to simplify this guy down into Z Thevenin, right? Here's my voltage source. Current would go this way, right? I test. So if this is V test, this is true about this circuit. Okay. Now I'm going to do in this case, what? I'm going to do the mesh method and I'm going to do them clockwise. So this is, I'm going to call this IA and I'm going to call this IB, like that. You guys follow me? All right.
Yep.
That tells me right now I test is equal to negative IB. Okay. All right. So let's keep going with this. So I have, here's Z1, V1, Z2, V2, 0.5 I naught. Okay. Now in this case, do I do both meshes here? No. I don't do both meshes, and this was I naught here. I don't do both meshes. Why not?
Because of that source.
IB is a test.
Because I got a current source here, right? If I got a current source, so where's the current source? I don't have a current source, do I? Where's my current source?
Dependence.
I got a dependent current source.
Yeah, sorry.
That still counts. That still counts as a super mesh, right? Because I got a current source. I don't have any way to relate current and voltage across that device. All right. So in this case, I got a super mesh. So if I have a super mesh, I need to figure out what the relationship is between the currents that super mesh or that current source sits between two meshes, right? So in this case, I say 0.5 I naught. I always start right there. 0.5 I naught equals what in this case?
A,
IA minus IB. Let me make this. I don't know. I'll do it this way with uppercase. All right, guys, follow that? That part's pretty straightforward, I think. Okay. Now, in this particular case, I can simplify this down pretty quickly, right? Can I? What do I? So I naught is the current flowing from top to bottom on Z1 right there. Okay.
So it'd just be negative IA.
Negative IA. So I see 0.5 times negative IA equals IA minus IB. Okay, like that. This guy becomes pretty easy to solve, but I kept it in matrix form here at the end. So I basically turned this into 0 equals 1.5 IA minus IB, like that. You guys follow what I did there? All right. So now, same thing. I don't have to worry about, let's keep this guy simple. Here's V1. Here's V2. All right. So to do this, I got my super mesh. I'm gonna forget that the middle guy's even there. And I'm just gonna look at that picture right there. Well, I don't want to forget that he's there. This is IB. This is IA. Okay. So let's do my super mesh. So super mesh, if I write a mesh equation, I write a KVL or a KCL?
KV.
KVL. All right. So my KVL equation, again, I always start in the bottom left corner and I say 0 equals, how do I write this in terms of the voltages? 0 equals what?
negative V1 plus V2.
Negative V1 plus V2 plus, this guy was a 1 volt source that I applied. So I say plus 1. Okay. All right. So in this case, I'm going to say minus 1. I'm going to bring the minus 1 over. Minus 1 equals minus, I'll say it this way, V2 minus V1. Okay. All right. So looking at it this way, what is V2? How do I put a current into that expression for V2?
IA Z2.
IA times Z2. And what about V1?
And negative I.
Negative IA. So minus negative IA times Z1. Right? I got a double minus that came in there, right? Because I had a negative that came in from writing the KVL. And then I had a negative from the fact that a current flows out of the plus terminal on that impedance. That's just my passive sign convention. So that becomes minus 1 equals IA times Z1 plus Z2, like that. Okay. Again, you guys might like to jump straight away to this statement here. My suggestion is not to. All right. My suggestion is to take it slow. All right. Don't try to skip steps. It's like when you learned algebra, right? You didn't try to combine all the steps together when you first learned algebra. Maybe you did, right? But you got stuff wrong when you did that. Okay. All right. So the way that I look at this is I've got two equations now. I've got 1.5. Well, I'll do it over here. All right. I've got 1.5 IA minus IB equals 0. That was the equation I got on the first slide there. And then I got this one that said Z1 plus Z2 times, which one was it? IA plus 0 times IB equals 0, or no, -1, like that. Okay. And I put that in matrix form. Okay. That's what I did. All right. And then I solved here for that. Okay. So again, this bottom equation is pretty easy to do. I could pretty easily solve for IA from that equation and then plug that in to solve for IB. All right. So when I do this, I'm going to get an answer for, if I run this code. Okay. All right, here's that code. So when I run this, I is basically going to have 2 elements in it, right? So if I run this thing, all right, there's my 2 currents. All right, IA is the top one, IB is the bottom one, right? So if you look at it this way, if I put this in matrix form, right, it would be 1.5 minus 1, Z1 plus Z2, 0 is IA, IB equals 0 minus 1, like that, right? So the second entry is IB, right? So when I look at my code here, or the output of my code, this guy has 2 entries. So I of 2, the second entry, is the current that I get there, all right? Now, notice what I did in my code to find Z Thevenin. I did -1 over that second entry. Why did I do that? Why minus?
-1 volt.
No, right? I applied a 1 volt source, right? Back to this picture, I applied a 1 volt source. This picture tells the story, doesn't it?
Yeah, because I test
Passive sign
from
convention.
negative side.
Yep, I test is the current, I test is always defined as the current flowing out of this guy. It's the opposite of my mesh current, okay? Now, in circuits 1, that wouldn't have been a problem. You would have gotten a negative resistor. You would have just made it positive, right? And you would have been fine. You know that you don't have negative resistors. When I have impedances, that's not true anymore, is it? What's a -1? Well, -1's adding 180 degrees. Okay, by multiplying by -1, I'm multiplying by 180 degrees now, right? So think about it, -1 is equal to 1 angle 180 degrees, right? It's on the other side of the number line.
Is it also correct, because I just see I test that's flowing through the -1 volt, if you will.
Well, it's just
defining the polarity.
yeah, but the important thing here is what I've shown on the slide right there, right? So I test is defined as the current leaving that thing. So it's not as clear as I'll get a negative number now, right? And just make that number positive. You have to think about it when I'm doing impedance here. So if I'm solving for a mesh current that's going the opposite direction of the current going in, then I'm gonna have to think about that. All right. And so in this case, what do I get as the answer? So Z Thevenin is unrecognized because I didn't compute it. I left that line out. All right, so Z Thevenin is that. All right. So let me ask you this question. Z Thevenin is 4 minus 2/3 I. So if I think about what that is, that's a 4 ohm resistor, isn't it? Right? So if I think about what that is, that would be a 4 ohm resistor. So I got 4 minus J times 2/3. Right? So I could say that this is a 4 ohm resistor, right? The real part, resistors are always real. Capacitors and inductors are the imaginary parts, right? So if I had minus 2/3 J, what kind of device is that minus 2/3 J?
Capacitor.
Be a capacitor, right? Minus 2/3 J. And I could figure out what value that capacitor is by knowing that 1 over J omega C is equal to negative 2/3 J. And if I know what omega is, I can solve for the C value, okay, if I needed to. All right, that idea becomes a little bit important when we talk about power, right? But it says that this guy apparently has an equivalent impedance that looks capacitive looking into it, Okay. All right, so we got more examples to look at, but we're sort of out of time for today. We'll pick up with this example on Wednesday. All right. So at this point, I'm kind of done, rehashing stuff. So we're going to do examples today. We're going to do examples on recitation. Oh, we're going to do examples Wednesday, and we're going to do examples in recitation on Friday. And I may do one more day of kind of examples on Monday, but then we're going to move on to new topics. Okay. We don't need to rehash these things a million ways, right? You guys know a lot of stuff at this point. In a lot of ways, we're just kind of synthesizing things that you already know. All right. So it's not that big of a deal, hopefully. All right. And we're just trying to make sure that you really polish it. Okay. All right. Questions that you guys have online.
Yeah, I had a quick question.
Okay.
How did you know what value to use for your test source? Like, I mean, I know you use 1 volt, but is it
Yeah.
always like that, or?
No, well, you can use whatever value you want. If I use 2 volts, right, then that's fine too. But the current would have been twice as big if I used a 2-volt source. So it would basically divide out.
So is it safe to say, like, just use 1 volt for these examples, or will there be a
Yeah,
situation where it's better to not do that?
You could always use 1 volt. That's fine. Or 1 amp if you use a current source.
Okay. Thank you.
Yep.
I had a question. Once the impedance is calculated for a resistor, resistor and a capacitor, as well as a resistor and an inductor, you can't add those together in any way. Can you?
You can add impedances in series and in parallel the same way you do with resistors.
Okay.
So if I told you I had, this circuit here, here's an inductor, here's a resistor, here's a capacitor. If this is ZL, this is R, right? And this is ZC, I could totally say the total here is this. Like that. Which would be
Okay. So then why
R.
didn't we?
Go ahead.
Yes, sorry, the dog. Why couldn't we add Z1 and Z2 on our example then?
That's a good, because there's no combination there. They're not in series or anything per se, right? When I look at this picture here, Z1 and Z2, are they in series?
Well, no, because
They have different currents, right? So there's no way they're in
Yeah.
series. And are they in parallel?
no, because they wouldn't
No.
be sharing the voltage either. Okay.
Yeah, they're
I
both,
see.
they share a terminal, but they don't
Yeah,
share a
okay.
second terminal, right? So their voltage across them is not in parallel.
Okay.
Voltage across 2 elements has to be the same for them to be in parallel. That current
it.
source is screwing this up in this case.
Okay.
Right. The voltage across the current source isn't necessarily 0. It has some voltage. We don't know what it is. The circuit tells us what it is. All right. Any other questions out there?
You said that you could use like a current source. Does it matter, or are there situations where a current source would be better than the voltage source when you do a test?
So it doesn't matter. So in this case, if I decided that I wanted to use, I could use either method, right? So if I had done the problem that we're looking at here, right, and I was given the original circuit. So if I'm given this guy, I put a voltage source in there because I wanted to use mesh. If I put a current source in there, I probably would have used nodal instead. And the reason I would use nodal is because I would probably want to solve for the voltage at this terminal and the voltage at this terminal. Right, think about that for a second. If I put a test source here of 1 amp, the thing I'm trying to find in that case is what's the voltage across here. So I'm basically solving for this node voltage. So if I had put a current source in there, I would have done the nodal method.
Oh, it's just like whatever method you want to do, basically.
Yeah. Yeah.
All right. Thank you.
Yep. All right. Any other questions out there? All right. Then I will close down. real quick.